All right, let's see. So we have three different amplifier or feedback amplifier topologies, I guess, to kind of talk about. Realistically, if I didn't work any example problems, we would cover all three today, but I think that would leave you guys more confused than it's worth. So let's start by looking at feedback current amplifiers, work an example problem or two with that, and then we won't do any example problems for the other ones because you will have enough knowledge to figure out what's going on. All right. So in a feedback current amplifier, we should expect that since our input signal is a current and our output signal is a current, our feedback network is going to be connected in parallel on the input side and in series on the output side. So in an ideal case, we are going to have something that looks like this. So here's our source current, IS. Once again, we are not going to have any signal resistance because we're dealing with an ideal case. So that's why I'm not putting anything in parallel with the source current. Here are the input terminals of my amplifier, or my open loop amplifier. So this is my signal VI. Here's my input resistance, RI, my current II. I'm going to choose to represent my open loop current as a current gain, A1, in parallel with some resistance R0. So think about this as simply nothing more than a source transformation on the practical voltage source representation that we had when we had a voltage amplifier, because that's exactly what it is. These are the output terminals of my open loop amplifier stage. Here's terminal O and O prime. Box around things here. Let's see. Down here will be my feedback network supports. So this should be K times I out, where I out is this current. And then to make sure that my feedback network does not load my amplifier stage, I'm going to have an open, excuse me, a short circuit on this side. And now we'll wire things up. This is my feedback current, IF. Our input resistance with feedback is measured looking in through between the S and the S prime terminals. And our output resistance with feedback, sorry that scrolled on me, is determined looking in to the through the O and O prime terminals. So simplified down to lump the feedback into our network. Oh, sorry, let me. That box is our feedback circuit. So simplified representation of this would be something pretty simple. We would have our input resistance RIF, AF, IS, where this is just our input signal current, ROF, like so. Here's our output current, I out, where not deriving anything, our gain with feedback would simply be the ratio of I out to IS, which would be A1 over 1 plus K A1. Our input resistance with feedback. So earlier we saw that when we connected in parallel, we attenuated our input resistance. So that would be 1 plus K A1. And R naught with feedback. Because we're in series, that should boost our output resistance. So that should look like R naught times 1 plus K A1. And all of those relationships can be derived extremely similarly to how we did for a feedback voltage amplifier. So now let's look at the practical case. So in the practical case, we might have some signal resistance. We might have some load that has an impedance. So instead of it being a short circuit, it might actually have a resistance. And our feedback network may load the input and output ports of our open loop amplifier network. So we would have something akin to this. So I sig in parallel with R sig. Here's the S terminal and the S prime terminal. This is our open loop amplifier circuit. Our load resistance. So put my feedback network down here. And this side is connected in parallel. Here's port 1. This side is connected in series. This is my current I out. This is also my current I out. And this is my current IF. This is my current I sub I. Sure. Input resistance with feedback. Output resistance with feedback. All right. So we have a diagram that looks incredibly similar to what we had for our feedback voltage amplifiers. So now we need to figure out effectively how our feedback network loads our system in order to apply the exact same process that we did with our prior amplifier. So I would like for you guys to go back to your notes and tell me what we did to find the resistance R22 for a feedback voltage amplifier. And the reason why I'm asking about R22 is specifically because port 2 was connected in parallel to the output terminals of that amplifier. So this is the same process is going to be used to determine R11 here. So when we found R22, and this was finding the loading factor when we had a parallel connection, we left both ports open circuited, looked into the port of interest. So we're going to do the exact same thing here, right? So finding R11, we are going to take our feedback network. Here's port 1. Here's port 2. We're simply going to look in with both ports open circuited, okay? Because that's what we're going to do every time our network is connected in parallel. Now, in this case, port 2 is short circuited. So how did we handle a short circuit connection last time? So previously we shorted 2 with 1 open. Now we're going to short 1 with 2 open because we're looking in from the other side, or our parallel, or excuse me, our series connection is on the other side of the feedback network, right? So here's port 1, it's shorted. Here's port 2, it's open. We look in to find R22. Okay. Our feedback factor we're going to do, again, something similar, but I'm going to go through this one in a little bit more detail on account of this time we're dealing with current signals on both sides. Let me put this here. The feedback. So here's port 1 and port 2. So we're going to apply a test source that I'm just going to call I out here. So that our current flowing into port 2 of the feedback network is I out, exactly matched with what we saw above. And then I'm going to short circuit this side. So when we had a feedback voltage amplifier, we had to make sure that the current flowing through it was 0. When we have this current amplifier, we need to make sure that the current, or excuse me, the voltage is 0. So we're forcing the voltage at port 1 to be 0, and here is our feedback current direction. And so K will simply be the ratio of I out over IF under the constraint that the voltage drop across port 1 is equal to 0. I'm sorry, I have that ratio backwards. It should be IF over I out. Did not have that written down. My apologies for that. So from this, our new open loop circuit is effectively going to look like this. So here is our open loop amplifier. We're going to have a resistance of R11 referred to the input side, a resistance of R22, sorry, this should be in series on the output side. Here is our resistance RL. Looking in here is how we find R naught, or the output resistance. Here is our signal resistance in parallel with R1, R11. Here is our input signal by sig. And looking into this set of terminals is how we find RI. So we now have all of the basic components, just like we had for a feedback voltage amplifier. So now let's apply this to an actual transistor-based circuit. Okay, so here's our example. I'm going to start with a quote unquote simple common source amplifier over here. So this will be transistor M1. The drain here will be connected to the gate of a transistor M2. And this will be effectively a source follower configuration, because this is behaving as a current amplifier. Let's call this resistor R1. This resistance R2. This is our input current signal, IN, and our output current is here. So just for the sake of argument, I'm going to define some things here. So looking into this node is how we're going to determine RIF, and looking in here is how we're going to determine R naught F. And what I'm going to do is I'm going to put these little X's. And so this is effectively telling us where we would break that connection and place our test source, okay? So this looks a little bit different than what we've done previously, and it's because we are taking a current as an output signal as opposed to a voltage as an output signal. So anytime we were measuring our voltage, it was across something, even across an open circuit. Here, we're breaking this connection, effectively going to place a test source in, and what we should see is that we'll have some resistance looking up on a path to ground and some resistance looking down on a path to ground, and those are going to be connected in series. That's the principal difference that we're going to see whenever we're looking at a current connection. And so whatever we see up in series with whatever we see down, because we're dealing with a current, whenever we had a voltage, it was whatever we saw up in parallel with whatever we saw down. Okay. All right. So what is our feedback network going to look like here? So I feel like this is probably one of the easiest ones to figure out because I've explicitly said where our input signal is, where our output signal is, and where we're breaking things to look at stuff. So I think that our feedback network is going to look extremely similar to what we saw in our feedback voltage amplifier. We are going to have a resistor R1 that's going between port 2, which is connected to the output of our amplifier, and port 1. So here we have our resistance R1. And then R2 is connected between the output side and ground. Anybody have any problems with that? Very, very similar, except that now the resistance that's across the port is on the port 2 side instead of the port 1 side because of where it is in our circuit diagram. So somebody please tell me what my resistance R11 should be. R1 in series with R2. What should our resistance R22 be? R1 in parallel with R2. Slightly more difficult. What should our feedback factor K be? So let's look at things here really quickly. I'm going to superimpose something on the top of this, right? So here's my current I out. Here's my current IF. And these directions are important, okay? So I believe that instead of having a voltage divider here, we're going to have a current divider network. Negative, absolutely. So it'll look like 1 over R1 over 1 over R1 plus 1 over R2, which is the same thing as just negative R2 over R1 plus R2. So just good old circuits 1 level current division. Nothing particularly wild or crazy there. Now, this is an interesting result because our feedback factor K is negative. So that means that our open loop gain needs to be positive in order for this system to have negative feedback. So think about all of our voltage amplifier relationship or feedback voltage amplifier relationships. Every time our feedback factor was positive, but our open loop gain was negative, so that it worked out for the negative feedback or everything to work out correctly. So this time, if we wind up getting a negative gain, we have positive feedback and instability. So just something to contextualize here. All right, so let's look at our open loop circuit. So it's going to look something akin to this. So here's VDD, RD, IN, R11, R22. Looking into here is how we will find RI. Looking into here is how we will find R naught, because I forgot to label it a second ago. Here's I out, R22, M2, and M1. So I feel like we're going to do what we've done other times we've seen cascaded amplifiers. Like I said a moment ago, this to me at least looks like a common source amplifier cascaded into a source follower amplifier. We're going to break it up into two stages, but this one we're going to kind of break up into three. So the output of our common source stage is the input spacing up here of our source follower stage. I'm going to call this voltage here at this node Vx, so that we can really treat that first amplifier as a common source amplifier, because a common source amplifier is a voltage amplifier, right? Not particularly a current amplifier. So what we're going to have effectively is a three-part gain configuration. So we're going to have Vx over In times Vy over Vx times I out over Vy. So let's start with the easiest part. What is the relationship between Vx and In? Yep. So all that resistance R11 is doing is converting that input current into a voltage. If this were a BJT, it would be a little bit more difficult, because we would, well, not that much more difficult. It would just be R11 in parallel with R pi, right? But nothing too particularly wild or crazy there. What should Vy over Vx be? Let's say that channel length modulation, for the sake of argument, is neglected here. Common source amplifier, no degeneration. Negative GMRD. So figuring out I out over Vy is going to be a little more difficult here. So I out here represents a small signal output current. Okay. So let's think about things really quickly here. Okay. So what we have is a situation like this. So we have our voltage Vy being applied at the gate terminal. Here we have GM2 times VGS. The drain of transistor M2 is grounded. I don't know why I put R22 down here at ground. That doesn't make any sense. I apologize for that. And then our current I out is this. Current flowing through that resistor R22. So anybody have any problems with this small signal representation of just our output stage, everything to the right of that red dashed line? Seems pretty easy. Okay. So what's I out? GM2 times VGS. What's VGS? Exactly right. So if we move some things around and rearrange, what we'll find is that I out over Vy is GM2 over 1 plus GM2 R22. Putting things together, our open loop gain is just going to be, sorry, this should have been a GM1 over here. We are going to have negative GM1, GM2, RD, R11, all over 1 plus GM2, R22. What is our input resistance? Let me see if I can sneak it in right here. Ri going to be? What was that, Ethan? Thought you had said something. R11, because it's looking up. Yep. What is our output resistance going to be? So what do we see looking down? R22. What do we see looking up? Perfect. And now we can literally just plug these results into our equation. So I believe that we accidentally have negative feedback here, or excuse me, positive feedback here, because our A1 term is negative and our K factor is negative. So let's see if that makes sense, right? So the whole purpose of our feedback network here, so some portion of I out is going to wind up flowing to this node. So here is our feedback circuit. What is it doing? Kirchhoff's current law tells us that these two are adding together effectively. So it's making that voltage look larger and therefore giving us positive feedback. How can we fix it? Make M2 a PMOS transistor. That's it. Although technically with M2 as a PMOS transistor, now our second stage is no longer a source follower stage. It's a common source amplifier. So what we would wind up having is GM RD1 or negative GM RD1 times negative GM2 R22. Those two multiply by each other, the negative signs cancel out, and everything works exactly how we would. All right, so that is a current amplifier. So now let's look at a feedback transconductance. All right, so in a feedback transconductance amplifier, our input signal is a voltage and our output is a current, which means our feedback network is going to be connected in parallel on both sides. So I'm not going to bother drawing the big picture and getting it down to an ideal case, but we have some understanding of what that should look like already. It should be fairly intuitive that for a feedback transconductance amplifier, our gain with feedback is just going to be the ratio of I out over our signal input voltage, which will be simply A1 over 1 plus KA1. Our input resistance with feedback, because things are connected in parallel, is going to look like Ri over 1 plus KA1. And our output resistance with feedback is going to look like R naught or R out over 1 plus KA1. Again, just because we're parallel connected, our feedback network is connected in parallel on both the input side and the output side of things. Actually, I have made a mistake. So the mistake that I have made is that I said the output side is connected. Did I say they're both in parallel? They're both in series. Yeah. So instead, go back to my notes. Instead of transconductance, I'm going to be lazy. Transimpedance. And now this is going to be V out, and this is going to be I sig, and now I don't have to change anything. That one last apparently. Sorry about that. So everything else is going to be effectively the same thing that we've already saw. So let's just figure out how to find our loading factors, R11, R22, feedback factor K, and look at our open loop gain circuit, right? So let me put this. So this is parallel connection. All right. So finding R11. So what did we do when we had a parallel connection previously? So how did we find R11 for a feedback voltage amplifier? Because that was a parallel connection at the output side. Open circuited port 1, short circuited port 2. Short circuit here, look in here, R11. All right. R22 is a parallel connection. So we're going to do the exact same thing, except we're just going to swap the ports around. So port 1 is going to be short circuited. Port 2 is going to be open circuited. We look in. To find K, so on the input side, we have a current, and on the output side, we have a voltage. So on port 2, I'm going to apply some test voltage that I'm going to call V out. On port 1, I'm going to measure current. So I need to short circuit this guy. So here is the direction of my current IF. And so K is simply the ratio of IF over V out when the voltage drop across port 1 is held to be 0 volts. So my A1 circuit is going to look something like this. Here's my signal. Here is R sig in parallel with R11. Here is R22 in parallel with RL. Here's V out. RI is determined by looking in here. RO is determined by looking in here. our last amplifier that we're going to look at is actually the feedback transconductance amplifier, where both sides are connected in series. Okay. So my gain with feedback, so my input signal is going to be a voltage, my output signal is going to be a current for a transconductance amplifier. So this is going to be the ratio of the output current to the signal voltage, which should just be A1 over 1 plus K A1. My input resistance will be boosted because we have a series connection. So that's just going to be, sorry, RIF will be RI times 1 plus K A1. And R naught F will be R naught times 1 plus K A1. You guys tell me how we're going to find R11. So here's my feedback network. Both sides open. Look into port 1. What about R22? Both sides open. Look into port 2. What about finding my feedback factor K? So let's think about this really quickly. So what is my expected output signal for a transconductance amplifier? It's a current, right? So that means we're going to apply a test current here that I'm going to call I out. What's my input signal? A voltage. So I'm going to leave this side open circuited and measure some voltage VF here under the constraint that the current that is flowing into port 1 is 0. So our feedback factor K is just the ratio of VF over I out when I1 is constrained to be 0. What do you think our A1 circuit is going to look like? So let's put the open loop amplifier circuit here smack in the middle. So how should our sig be connected? Okay. How should R11 be connected? Sorry, too far. Series. Everything will be connected in series because it's a series connection. Looking in through here gives us Ri. Looking in through here gives us R0. So let's work one last example problem, and then this will be class done. Let's call this M3, M4. Here's Vn. Here's IS1 and 2. So our input resistance with feedback would be looking in through here. Our output resistance with feedback would be looking in through here. By the way, this is a laser amplifier. And I hope it will. Is what it is. Should go to class. No. All right. So somebody can draw my feedback network. This is the hardest one we've seen. As a joke, by the way. Okay. Something is not an open circuit.
Is it one over?
So that's it. That's our feedback network. There is a wire literally tying where we're taking our output current to where we are manipulating VGS and our input voltage. M5's gate. No, so that's our feedback voltage. So this is a two-stage amplifier where effectively the output of the differential pair is serving as the input of a, I'm going to call it a PMOS common source amplifier. Although there is that, the dynamic or the small signal resistance of that laser diode that we are going to have to take into account a little bit as well. So what's R11? This is the easiest possible one. RM. What's R22? Also RM. All right, so now what's K? So recall that we're going to apply a current on this side and measure the voltage here. Yes. Our input signal is a voltage. Our output signal is a current. This is a feedback transconductance amplifier. It's literally that. If our input signal is a voltage, our output signal is a voltage, it's a feedback voltage amplifier. Input is current, output is current, feedback current. Input is current, output is voltage, feedback transresistance, whatever. So this one is definitely transconductance on account of the input signal as a voltage and the output signal as a current. Feedback factor K. $1 million question. Actually, it's more like 5-cent question. Also RM. Absolutely. Yep, 100%. R11, R22, and K are all literally just that resistance RM. All right, so now let's look at our open loop circuit. Okay. I'm replacing the diode with its small signal equivalent resistance R gain. Since we're gonna analyze this thing, feel like that might be useful. Yes, sir. Sorry, they were supposed to stay PMOSs. They didn't magically change. I just wasn't paying enough attention. Thank you for that. M4, M5, R22, M1, M2. Well, thank you for that, Gabe. All right. So I'm going to call this node X so that our open loop gain overall should be Vx over L, and here is our current I out. So we should have Vx over V in, and then maybe an I out over Vx. Something akin to that. So what should Vx over Vn be? So if we ignore transistor M5 and we're just have this circuit and we're taking the output, actually we're taking the output to be at node X, what does this look like? It looks like an output, but it's a little bit different. What's different about it? We turned our current mirror around. Right, so previously we had tied, like if we had done this instead, I'll put this back in a moment, and then taken the output here, that would be our single stage op amp. But we're doing the opposite. What do you think that's going to do to our gain relationship? There was no, we're not worried about the feedback at all yet. Right, so it's just going to change the gain to be a negative of the exact same thing that it was. Yes. So negative GM1 R01 in parallel with R03. To sort out what's going on with our PMOS secondary stage here, the thing that's driving that LED, let's apply a small signal model like we did previous. So here's our voltage, Vx. This is the gate of 5. Our source was at ground. This is the drain of 5. Here's R05. And I think this should be the direction of our output current. So how are we going to relate I out to Vx? But first, does anybody have any questions about this small signal model? It's a PMOS device. I drew it like it was an NMOS device, but I made sure to use VSG and change the direction of the current source. Current division sounds perfectly reasonable. So we could say that I out is just going to be GM5 VSG5 times R0 5 over R0 5 plus RD plus R22. Or I'm using the fact that I have two resistances in parallel and I'm using the current through the branch I don't want over some of the branches instead of doing the reciprocal, just because that's just gonna be gross and messy. It's gonna wind up giving us the same result. Okay? That is literally the exact question I was about to ask, but yes. So if we put a VX here and we put a negative sign here, then what is I out over VX? Well, I think it's negative GM5 R0 5 over R0 5 plus RD plus R22. By inspection, well, let me put it on here really quickly. So here is where we would measure RI, and here is where we would measure R0. So what's RI? Infinity. Yay, that's easy. So to be real clear on our small signal model here, this is where we would wind up measuring R0. If our input signal is grounded, what is that going to make VX? So it is RD plus R22. What else? All of that in parallel with R0 5? I disagree. All in series. Yes.
Could I see the I in with the X?
All right. So we covered the last three feedback amplifiers today. So we are done with lectures for this class. I will be here on Monday and Wednesday and Friday of next week to answer any questions that you may have about your various assignments that are due. So consider the last week of class, as far as I'm concerned, optional, but I will definitely be around to give you guys any help that you need.